Okay, I think I can start to introduce you. So yeah, in the meanwhile, as people are coming in. So yeah. Okay, hello everyone. My name is Yan Chen. I'm the director of Siena. For the people who are first time to join our seminar, this will be the bi-weekly or monthly seminar of our AI Institute. Today our speaker is actually our PI, Professor Song Han from MIT. I believe many of us actually know him very well. His research focuses on the efficient deep learning computing, and he has proposed a deep compression as 2016, if you still remember, the way to reduce the neural network size by the order of magnitude, and also the corresponding hardware implementation on this. And that basically was the first model compression with the sparsity method in the deep learning society, considering this hardware constraints. And he received multiple best paper awards, including the ICLR 2016, IPG 2017, and then received the National Career Award, MIT Technical Review Certified under Certified, so on the first. Of course, there's a pruning technology, compression, and also some acceleration concept has been well received by the community and also integrated in many actually commercial semiconductor chips, accelerating the deep neural networks. And he received a PhD from Stanford. So, okay, so now I give the mic to So, and you can start. Yeah.
Hey, thanks so much, Iran, for the kind introduction. Good afternoon, everyone. Welcome to my presentation on TinyML and efficient deep learning, make AI efficient for edge devices. So today's AI is too big. The number of parameters is growing exponentially in recent years, and we need new algorithms and hardware for TinyML and Green AI to reduce the computation cost for AI and be able to deploy AI on resource-constrained devices. We need to co-design the efficient algorithms and efficient hardware to realize this goal. Recently, there is a trend for TinyML, which targets deploying deep learning on those edge devices, such as microcontrollers. They are also known as IoT devices, which has much smaller memory footprint, no operating system, which is running bare metal. So this is much more challenging than deploying conventionally the cloud AI and the mobile AI, where we have gigabytes of memory, but now we have only 256 kilobytes of readable and writable memory. There's also no operating system. There's also no like Python library support, and we have to manage all the resources by ourselves. However, there is a huge demand for these AI plus IoT, commonly known as AIoT devices. So how do we do this full stack design for this TinyML community? So before jumping to the techniques, I'll first show a demo that we can deploy AI on these tiny microcontrollers, not only classification, but also detection. For example, on the left-hand side, that is the face and mask detection. We can detect the person with a face mask on this Cortex M7 microcontroller. This has very little resource and super cheap, just $2 to $3. And on the right-hand side is doing person detection, drawing the bounding box for the person sitting far beyond, which require only about 320 kilobytes of memory. So I've done 2 generations of this line of work, which I will present today, including the MCUNet version 1 in NeuralReef 2020, and also the MCUNet version 2 in 2021. So the challenge is that the memory for these microcontrollers are too small to hold deep neural networks. There are plenty of research studying the mobile vision, mobile AI, like MobileNet, but it lacks the research for this tiny AI. And we find the key bottleneck of a neural network memory is actually the activations. So when we are doing a convolution, the input activation is convolved with the kernel and produce this output activation. So the kernel can be stored in the read-only flash. Okay, but the input activation and output activation needs they're both readable and writable memory. So let's compare the peak memory footprint of existing neural networks like MobileNet 50, ResNet 50 and MobileNet version 2. Their peak memory consumption is much larger than what we have in a microcontroller, which is only 320 kilobytes for STM32 746 microcontroller. But the existing work like MobileNet version 2 targets reducing the flops and the model size. However, the peak memory didn't get improved much. Compared with the ResNet 50, the peak memory only reduced by less than 10%. Okay, so there is a huge gap. Well, for MobileNet version 2, even if we quantize them to integer, the memory consumption is still 5 times larger than the memory constraint of a microcontroller. As a result, people can only do these toy applications on microcontroller, like classifying apples and oranges and bananas, which is very simple, can be simply done by looking at the color. So by proposing MCUNet, we expand the application broadly to real-life applications on large-scale data set like ImageNet, where we can achieve more than 70% top-line ImageNet accuracy on a microcontroller. So in today's presentation, I will talk about all the techniques that enable such tiny deep learning, including MCUNet, tiny deep learning on IoT devices, and the second version of that, MCUNet V2, memory efficient patch-based inference for tiny deep learning, where we can increase the resolution for these tiny devices by using the patch-based inference. And finally is a training technique called network augmentation for tiny deep learning. So for large networks, we augment the data. For tiny networks, we need to augment the network to improve the accuracy. So let's get started first with MCUNet. So conventional work like neural architecture search targets search a neural network model on an existing library. Okay, example including Proxylix NAS and NASNet, etc. Another line of work targets tuning the deep learning library given the neural network model. So the neural network model is fixed while we just change the inference engine, such as the TVM. So here, given the tight memory resource, we need to tune both. So we are proposing to co-design the neural network architecture search algorithm and also the tiny inference engine, okay, to design efficient neural architecture and also the efficient compiler and runtime forming a loop. By such co-design, we open up a much larger design space to auto-optimize the neural architecture and also the inference engine. This is particularly important for microcontrollers since it has no operating system, no Python, no other runtime support. So let's first introduce TinyNAS, a two-stage neural architecture search for tiny memory constraints. So the goal is to replace human rather than manual architecture design. We want to use machine learning to do automatic architecture design. So NAS has existed for a couple of years, but people usually focus on optimizing given design space. This is very well known for mobile AI and also for cloud AI. But for tiny AI, there doesn't exist a good design space to begin with. So this is a very blank area to research, like given only 30 kilobytes of SRAM, which is a better design space. For example, we can either use a width of 0.3 multiplier or a resolution of 160, or we can use a larger width multiplier with a smaller resolution. Which design space is good for a microcontroller? But there is no prior expertise on MCU model design. So here we first apply this memory and storage constraints to have a optimized search space, and then perform the neural architecture search on this optimized search space. To be specific, we propose a method to analyze the flops distribution of the satisfying models in each search space. So here, each colored line is a search space, The x-axis is the flops. The y-axis is cumulative probability, saying that by satisfying this kind of flops, how much percentage of the model can fit the memory. Okay, so our intuition is that a good design space is more likely to achieve high flops under a fixed memory constraint. This is given the fact that memory is expensive and computation is cheap. The memory is a hard constraint, flops is a soft constraint. So given a limited memory constraint, we want to achieve as much as computation as possible to amortize the memory overhead, okay, data movement overhead. So let's see two examples. So this red curve, okay, the red curve is one design space corresponding to width multiplier of 0.5, resolution of 154. Okay, so using this design space, we sampled many designs. Okay, so for 80%, more than 80% of the models, the flops is more than 50.3 million. Okay, but given the black design space, which has a width multiplier of 0.3, a resolution of 160, more than 80% of the models has flops more than 32.3 million. Okay, so of course, this red dot is better than this black dot. Okay, fetching the same amount of memory, we can achieve more computation on top of it. And that's indeed the case. The best accuracy we can achieve on this red line is 78.7, but on the black line is only 74.2. Okay, so without any training, we find that this comparison of flops given the memory constraint is a very good approximation to select the design space. Okay, so this is one of the highlights, how to design this design space given a fixed memory constraint, using the intuition that larger flops, meaning we have larger model capacity and it is more likely to give a higher accuracy. And second, after finding a good design space, we can perform a NAS, which is a resource constraint model specialization. So here, basically, we use the once-for-all network to do the architecture search. It is a one-shot NAS through weight sharing. During training, we random sample different subnetworks, and then we jointly fine-tune both the large model and also the subnetworks all together. And as a result, we can design neural networks of different capacity. We need to train only once, and then we can have those small child networks nested in larger ones. So on different microcontrollers, we can use different subnetworks. Like for a Cortex M7, we can use a larger subnetwork. For Cortex M4, we can use a smaller one. So by using this approach, let's investigate what is the model size and activation size. So conventional methods like MoveNet V2 targets at improving the model size, the number of parameters. We call it model compression, right? But actually, the activation, which is the real bottleneck, didn't get improved, but actually decreased. So compared with Resident 18, and also comparing Resident 18 with MoveNet version 2, 0.75, they have the same accuracy, like 70% ImageNet top-line accuracy. MoveNet V2 0.75 successfully reduced the parameters by 4.6 times. However, the peak activation didn't decrease, but actually increased by 80%. So this is a missing point for conventional efficient model design, in which people neglected the activation size. By MCUNet, which we can also achieve 70% ImageNet top-line accuracy, we can decrease the peak activation by more than 3 times compared with MoveNet V2 0.75. Okay, so another part is that TinyNAS can search the models, can better utilize the memory. Okay, so we investigate the peak memory for the first 2 stages. So MoveNet V2 and TinyNAS, they have a highly imbalanced feature. Okay, so for MoveNet V2, the peak and also the average, this difference is much larger. But TinyNAS, is more flat. Okay, it's more flat since the memory is dominated by the largest bar. So TinyNAS can better utilize what we have. So here, the max versus the average is 2.2 times for MobileNV2, but for TinyNAS design models, it's only 1.6 times larger. So TinyNAS design networks with more uniform peak memory for each block, so allowing us to fit a better model at the same amount of memory. So we didn't explicitly put any prior to encourage such balanced design, but the TinyNAS can automatically find such model by encouraging the good trade-off between the accuracy and computation. Okay, so having talked about the TinyNAS, I'm going to talk about the second part of MCUNet, which is the TinyEngine. It is a memory-efficient inference library co-designed with the neural network model. The first highlight is that we want to reduce the overhead of the runtime overhead with separated compilation and runtime. Okay, so existing deep learning libraries such as Google's TensorFlow-like Micro or ARM's CMSIS-NM, they are based on runtime interpretation. Okay, so everything is such as the meta info, the memory allocation, all the supported OPs has to exist in the runtime, which leads to a lot of computation overhead for the interpretation, and also a lot of storage overhead for those unnecessary operators, and also memory overhead for those meta info. So what we are doing here is to push as much as the computation into compile time rather than runtime. So we push the memory scheduling decision into compile time, and also only compile those specialized OPs that is going to be used in our neural network, and remove all the redundant OPs. So this is really pruning the number of OPs in our binary so that we can reduce the binary size. So at the inference time, we only need to perform the actual inference. So by using this technique, we can reduce the peak memory from 160 kilobytes to only 76 kilobytes, about 1.7 times smaller by using this compile time model adaptive code generation. The second technique we use is the in-place stepwise convolution. Okay, so the dilemma for this inverted bottleneck is that we need 2n peak memory. N is the number of channels. Okay, since the input activation and output activation, they have the same number of channels. Rather than writing it one by one, we propose this in-place stepwise convolution, which only use one temporary buffer for each channel. As a result, the peak memory is n plus 1. So when n is pretty large, this is almost 2x saving of the peak memory. So we further reduced the memory consumption from 76 to 48 kilobytes. To achieve faster inference speed, we analyzed the median max per second improved by each technique. So by changing from code generator-based compilation into, by using this code generation-based compilation, we can eliminate the overhead of the runtime interpretation. So this improved the median max per second from 52 to 64. And on top of it, we performed model adaptive memory scheduling to improve the data reuse for each layer. So by model level memory scheduling, we want to examine what is the largest kernel size square times input channels to determine how much buffer we are going to allocate. This is neural network specific, which means it is co-designed with our neural net, since it depends on the kernel size and the channel number. And then the number of tiling size will be determined by the buffer size divided by the current layer's kernel size square times input channel. So by using such a specialized image column, we can increase the data reuse, better cache locality, further improve the throughput from 64 to 70. And next, we performed operator fusion to fuse the padding, convolution, ReLU, and bin together with a single specialized kernel to minimize the memory footprint, which improved the throughput from 70 to 75. And next, we performed loop unrolling to have less branch prediction overheads, since the microcontroller has very poor branch predictors. So by having loop unrolling, we further improve the throughput from 75 to 79. And finally, we performed the tiling. Tiling loops, they are based on the kernel size and available memory. To have this specialized loop unrolling and tiling according to the network architecture, all these three techniques improved the throughput from 70 to 82. So these techniques is model specific, so that's why it is neural network and inference engine co-design. So put them together by applying various techniques, we can reduce the peak memory by 3.4 times and improve the throughput by 1.6 times. So by comparing with TensorFlow Lite Micro, the tuned micro TVM, and CMSIS NN, TinyEngine can reduce the peak memory by up to 4.8 times and improve the speed by up to three times faster. So we experimented with a couple of real-world TinyML applications, such as the audio wake words, Google Speech Command, and also the visual wake words to detect whether there is person or no person. We also scaled it to 1000 class, the full ImageNet classification. So here we have the baseline, which is the MobileNet V2, scaled it to 30% with a resolution of 80 to fit this STM32 F746 microcontroller. It has only 320 kilobytes of SRAM and 1 megabyte of flash. So by using this scaled MobileNet V2 and ARM's CMSIS NN, we can achieve a top-line accuracy of only 39%. By using system-level optimization only, replacing CMSIS with TinyEngine, we can improve the accuracy to 49%. You may ask why here we can achieve higher accuracy just by changing the inference engine, because this inference engine is more memory efficient, which can fit a larger model now. So the weight multiplier increased to 0.35, and the resolution now we can fit a 144 by 144 image. So that's why we can improve the accuracy by 10%. These days, every 1% of accuracy improvement on ImageNet is difficult, but on the TinyML settings, this is still a very blank, less well-studied area. So we can improve it by like 10% and then another 7% on top of it by using TinyNAS to design the best fit neural network given the inference engine. And the best solution results from the co-design of TinyNAS and TinyEngine, which further boosted the ImageNet accuracy to 62%, which is a huge improvement on top of the baseline model. So by using the once-for-all approach, we can easily handle diverse MCU microcontroller platforms. So including the Cortex M4 and also Cortex M7. The SRAM ranges from 256 kilobytes to 512 kilobytes. The flash ranges from 1 megabyte to 2 megabytes. So we can, the largest model, we are the first to achieve more than 70% ImageNet, 1000 class ImageNet accuracy on commercial microcontrollers. So just to look at the history, to achieve 70% ImageNet accuracy, in 2014, VGG achieved that with 70% on a desktop GPU. And 3 years later, okay, in 2017, people, by using MobileNet, people can achieve 70% microcontroller on a cell phone, on a mobile phone. And this was in 2020, another 3 years later, we can achieve 70% ImageNet accuracy on a tiny microcontroller. So every 3 years, the models are getting smaller and smaller, more and more efficient. This is the inverse Moore's law, where we can design smaller models to achieve the same accuracy. And later, we will continue to see in 2021, we can further shrink the model. This is just a comparison of using existing industry techniques like MobileNet V2 plus ARM CMSIS, and this is the best accuracy we could achieve at that time. So by MCUNet, introducing TinyNAS and TinyEngine, we can improve ImageNet accuracy by 17%. So here are some improvements on the visual wake words, just showing the consistent improvement of latency reduction and memory reduction for these tasks. And also audio wake words speech command dataset. This is also we achieved a consistent 2 to 4 times reduction of latency and SRAM usage. Okay, so in summary so far, from cloud AI, where people design the ResNet, and then for mobile AI, people design the MobileNet, and for Tiny AI, now we believe MCUNet suggests that the era of tiny machine learning on these IoT devices has arrived, and we can do a lot of non-trivial tasks and open a broad picture that there's a lot of imagination we can possibly do with such a small amount of memory resource constraint, so that with a very low budget, with low power, low resource, we can do a lot of real world vision applications. This can also potentially benefit those economically disadvantaged population to democratize AI to be very cheap and very affordable. Okay, so so far we are still targeting very small resolution. Okay, so how do we improve the performance, decrease accuracy, so that we can do not only classification but also detection tasks?
Song, there is a question in the chat. Do you use the same data set for your architecture search as your accuracy testing?
Yes, we use the same data set for architecture search and also the architecture testing. We all use the ImageNet for architecture search by training the once-for-all network. By the way, the code is available on our GitHub if you want to see the details, how to train, how to search the architecture using once-for-all on ImageNet.
You see that is a limitation. What happens when you use a different test, when you do an architecture search on ImageNet and then use a completely different data set for accuracy testing?
Actually, that works very well. So the architecture was searched on ImageNet, and we can, this result, the accuracy result is also reported on ImageNet for the search model for testing. And also it transfers very well to other tasks like the visual wake words task, and also achieve the significant inference latency speed up and better accuracy latency trade-off. Although the model is searched on ImageNet, but it transfers well to other downstream tasks like visual wake words dataset. Okay, so let's continue to talk about the MCUNet version 2. Okay, so MCUNet version 1 basically introduced the Tiny NAS, designed the design space before architecture search, okay, and the Tiny Engine. Okay, the problem here is the insufficient and imbalanced memory utilization across the blocks, and also leading to poor performance on applications beyond classification, like object detection. So how do we also be able to achieve object detection on microcontrollers, which is a huge moonshot? So we examined the memory distribution of the CNNs. This is the per block memory usage of MobileNet version 2. Okay, so we can see this is highly imbalanced. The peak memory is dominated by the third block. Okay, and all the future blocks can very easily fit this 256 constraint of a microcontroller. Just the first couple of blocks is above this constraint, which make it very hard to fit the neural networks on a microcontroller just due to this first couple of blocks. If we compare the peak versus the later stage, the average, it's actually 8 times larger. So this is a very poor design. And why we have been using this design for many years, like from MobileNet v2 to today, we have been using this model. That is because a mobile phone, which has like 4 gigabytes of readable and writable memory very easily, this doesn't quite matter if we have a peak memory of 2 megabytes versus 200 kilobytes. Okay, it's very small margin. But on a microcontroller, every 1 kilobyte counts, and we have only 256 kilobytes. So now it becomes a new challenge. Therefore, that's why I'm saying the tiny model design and mobile model design is fundamentally different. So we need a completely new design methodology to deal with this issue. And similar techniques, similar observation, similar problem is observed on MNASNet, where we have this third block dominates the whole memory. And similar for the FBNet, also the third block significantly dominates the other blocks by 6 times. So our goal is to redesign the model, okay, and redesign the inference schedule to reduce the memory usage of the initial stage and reduce the overall memory usage. So if we can cut the memory usage by using this patch-based inference, we can actually cut the inference memory from this dashed line to these solid blue lines. So the new peak memory can very easily fit this 256 kilobytes of microcontrollers constraint. So let's see, how does the patch-based inference work? So normally when we are doing a convolution, we are convolving a input tensor, which is H by W by C channels with a kernel, and both the input and output has to reside in the SRAM memory. And weights can be fetched from flash, which is read only, okay, for the microcontroller. And the flash is roughly 1 to 2 megabytes, which is not the bottleneck here. So let's compute if using conventional per layer inference, the peak memory include both the input and output activation, which equal to 2 times W times H times channel. Patch-based inference basically cut the input image in the XY dimension. Say if we use 2 by 2 based patch-based inference, the peak memory is only 2 small w small h times c, which is much smaller than the original one. So we just compute each patch one by one, and only 1/4 of the memory is needed. And of course, we can use larger sized patches like 3 by 3 patch. So by comparing the per layer inference versus the patch-based inference, we can find the per layer inference is always equal to the input activation plus the output activation. But for per patch-based inference, we don't need to hold all the input, but only need to hold like 1/4 of the input and output. But for the final stage, we need to hold the entire output. Luckily, due to downsample, this stage can have a much lower resolution. Therefore, even if we hold the entire output due to the much smaller resolution, it doesn't account for much memory. So we can watch the video again. Okay, so for this neural network, we can, if we perform this per layer based inference, we need a peak memory of more than 1 megabyte. But by using per patch based inference on the first 4 or 5 blocks and per layer inference in the later blocks, we need a memory of only 172 kilobyte, which effectively reduce the peak memory by 8 times. However, if we naively do this, it has a problem. Okay, so say this is output activation. When we have a stride, there will be overlap between the receptive field that computes this output versus the blue output. And the overlap can get larger and larger when we have gradually populate backpropagate the input the receptive field to earlier layers if we're using this patch-based inference. So this actually brings extra computation overhead due to the spatial overlapping, which will get larger as the receptive field grows. So now we are incurring larger computation overhead, although we are shrinking the memory. So here we are treating the memory, treating the computation for memory. So can we get the best for both worlds without any overhead of the computation? So we first plotted the overhead due to the patch-based inference is roughly 10%. But we propose a network redistribution, and we can reduce the receptive field for the earlier stages and increase the receptive field for the later stages that does not use the patch-based inference. So the overall receptive field from output to the input stays exactly the same. But we just redistributed the receptive field from patch-based inference to per layer-based inference, which effectively reduce the memory, reduce the computation back to its original size. Okay. So it has the same inference performance on image classification and object detection. So no hurt of the accuracy, no overhead for the computation, but just a free lunch to improve the memory consumption, which is a very cool technology to targeting reducing the memory consumption. It is definitely not mathematically equal because we redistributed the receptive field. But that's the beauty of neural networks, where even it's not mathematically equal, by training them, by designing new architectures, we can keep making new innovations and fully match the original accuracy. And finally, this is a pretty large design space. Like how many patches do we use 2x2 patch or 3x3 patch? How many layers are using patch-based inference versus layer-wise inference? And other design knobs in TinyEngine, we put them together and performed this neural architecture search to automate this design process. And that borns this MCUNet V2. So let's first look at the contribution for this network redistribution and with patch-based inference. So with 2x2 patch on this MobileNet V2, MobileNet V2 redistributed version, FBNet, MCUNet, we can effectively reduce the memory by 2 to 3 times. By using 3x3 based patch, the theoretical saving is about 9 times, and the measured saving is about 4 to 5 times memory saving. And these are measured on STM32F746 MCU using the TinyEngine baseline. And also, we want to see the ImageNet classification results. So this is doing large-scale ImageNet 1000-class ImageNet classification, quantized to int8, served using TinyEngine. From MCUNet to MCUNet V2, we can improve the accuracy by 4.6 times due to using the patch-based inference effectively reduced the memory consumption. So given the same amount of memory, 256 kilobytes, we can fit a larger model and achieve higher accuracy. Similarly, on the Cortex M7, previously this is Cortex M4. Now using Cortex M7, 320 kilobytes of memory bottleneck memory budget, we can effectively improve MCUNet accuracy by 3.3% to MCUNet V2. So again, this is the result also on the visual wake-words, just to show the architecture not only work well on ImageNet, but the same architecture also work well on other tasks like visual wake-words. So on the right-hand side is showing that peak SRAM can be reduced by 4 times from MCUNet to MCUNet V2. And on the left-hand side is showing the accuracy versus the memory trade-off. Okay, so the yellow line is our 2019 result. The proxy is mass, ICR 2019. To achieve like 88% accuracy, we need 256 kilobytes of memory. So this was the winning solution in the CVPR tiny visual wake-words challenge. 1 year later, in MCUNet, we pushed it to 128 kilobytes with even better accuracy, like 90% accuracy. By MCUNet V2 will further push it by 4 times smaller, okay, from 128 kilobytes to only 30 kilobytes, and with even superior or same level of accuracy. So to give a short summary here, the TinyML targets designing those light-weighted neural networks and deploy on cheap devices that has low power, low computing, and low memory. This is very beneficial for AIoT applications where now we have billions of these IoT devices based on these microcontrollers They are much cheaper, like $1 to $2. They exist in our refrigerators, in our washing machines, dishwashers, everywhere. They are everywhere, but they suffer from memory constraint. The MCU9 V2 propose a patch-based inference method and can effectively reduce the memory and pave the way for tiny machine learning on these edge devices. Okay, so having visited object classification, image classification, let's look at object detection. So a key bottleneck here is that resolution matters a lot for detection compared with classification. So this yellow curve is the ImageNet top point accuracy. When we are changing the resolution from 352 to 160, the accuracy drops slowly. But for detection, which is this blue line, the accuracy drop degree is much faster than classification, indicating that object detection really need a higher resolution in order to be able to detect objects of different sizes. So object detection is more sensitive to the input resolution. And the patch-based inference method proposed in MCU9 V2 allows for such a larger resolution and improve the detection performance. Like this is MAP on Pascal VOC dataset for object detection. MobileNet V2 plus ARM-CMSysN can achieve 31.6 MAP. MCUNet achieves 51, and MCUNet V2 achieves 68. This is a pretty large improvement of the MAP for detection tasks. Well, all of them are feeding a memory of 320 kilobytes. And we can see some visualizations for face detection on the wider face data set. For example, the side face cannot be detected by previous work, but on MCUNet, it is detected. And there's also no misprediction. Similarly, for this figure, this little boy can be successfully detected.
Song, there is another question in the chat. Why should detection require higher resolution than classification?
And classification, for example, to do a classification, we just need to see what is exactly what is in the image. But for detection, we have to not only give what it is, but also where it is. Some objects could be quite small, like for this region. Something can be mispredicted. We have a very low number of pixels. Since we have to not only give what it is, but also where it is. And the location of the bounding box also matters. Okay, so let's now look at to dissect the MCUNet V2 architecture to understand what are the design insights, why it can have such good performance. So the dashed line are using the per patch based inference. We can see that the earlier, when we have higher resolution, we are using per patch based inference. When we have lower resolution, we are using the per layer based inference. Okay, this makes a lot of sense since per patch based inference is like slicing a pizza. When you have a pretty big pizza, when you have a pretty big resolution, like a large pizza, we want to divide it into several chunks, okay, so that we can easily eat it and digest it. And also we choose to use this the kernel size in the per patch based stage is pretty small, okay, to reduce the spatial overlapping. This makes a lot of sense since we are talking about using the patch-based inference will lead to overlap, which leads to more computation overhead. The spatial overlap is either due to a large kernel or due to downsample. Okay, for downsample, we have moved the receptive field to a later stage. For the kernel size, we use the smallest possible, which is 3 by 3, to reduce the spatial overlap. And by the way, these choices are not human design, but it's purely the observation that we find afterwards from this neural architecture search model. We also find the NASD model finds that the expansion ratio in middle stage is small to reduce the peak memory. Okay, since these stages doesn't have any patch-based inference, so we have to keep the expansion ratio small to reduce the peak memory. And they are larger to boost the performance. Since in the larger layer, the resolution is already pretty low, it doesn't quite hard to have a larger expansion ratio since it's not the bottleneck. And also the larger input resolution is now be able to accommodate it. Previously, MCUNet can fit 128 and 128, but MCUNet V2 can fit 160 and 160. So finally, this is a
detected by our
video
model.
demo for MCUNet for detecting person and also detect person in multiple postures. And also can do person detection by just sticking it to the wall, and it will be red if it observes there's a person, or it will be green if there's no person in front of the camera. We can also put it in the elevator and detect if a person appears in the elevator. It's pretty small, pretty tiny, very low power, very, very portable. And also it can be used to help detect whether a person is wearing a mask or no mask. I have many hundreds of such devices in the building at a very cheap cost. Okay, so we talk about two techniques for improving the accuracy of TinyML. And now let's switch gear from inference to training. Oh, by the way, a question about what hardware are you using in the demo? So here we have a short introduction of the hardware we used in the demo.
Running on OpenMVCam with Cortex.
So this is ARM Cortex M7 microcontroller. It is called OpenMVCam. So you can order it online. It is very small, similar size, maybe even similar size as the Apple AirPod. And this is the hardware that we have. OpenMVCam. There's another question. So your classification task implicitly assume detection has already been done. No, the classification task doesn't assume any detection task has been done. It's the standard ImageNet classification. Okay, so given the time, let's finish the last chapter from inference to training. So we propose the network augmentation for tiny deep learning. So imagine, let's re-examine what are the techniques to boost the performance for large models. We need to perform data augmentation to reduce overfitting, or doing cutout to remove some part of the image, to mix up to have a linear combination of the image versus the prediction. Auto augment, try to add some different policies to jitter the input image, or we can do dropout to prevent overfitting. Okay, including spatial dropout, block dropout, etc. All these techniques are basically adding noise to the data set, like data augmentation, to avoid overfitting the training data. And this works very effectively on large models like Resident 50, the baseline model. Accuracy can be improved by mix up, by auto augment, by job block. But surprisingly, it actually hurt the accuracy for these tiny settings, like Mobile V2 Tiny. The accuracy is deteriorating after applying these techniques. And the key reason is that these tiny models is fundamentally different from large models, where it has a very low capacity, like only 23 millimax compared with the 4 gigamax. So with such low capacity, we should not augment the data, but we should augment the network. We augment a tiny network to be a larger network. Okay, augment the model to get extra supervision during training for tiny models. Say during optimization, if a smaller subnetwork gets stuck in a local minimum, the extra supervision, we hypothesize that the extra supervision can help it get away from the local minimum. So the way we do that is initially we train this model backward, forward and backward the same way as we did before. And now we build an augmented model, okay? And also do back propagation on the augmented model to get the gradient for this augmented model as well. The augmented model contains the base, which is base weight, which is shared with the original model, plus these augmented weights, which is actual supervision, which is the actual weight. And at learning time, we add the gradients together to get a total gradient. Not only the gradient of the model itself, but also the gradient when the model is acting as a subnetwork in a larger network. Okay, so in this way, we can effectively augment the capacity of the model. We can either do it in the width dimension, or we can do it in the by augment the expansion ratio dimension. So this way, we can effectively improve the imaging accuracy for many tiny neural networks, like MomentMV2 Tiny, MomentMV3, Proxyless NAS, and MCUNet. And this is also orthogonal to knowledge distillation. Okay, this method can be combined with knowledge distillation to further boost the imaging accuracy. And one interesting observation is that in the learning curve of tiny model, okay, the training accuracy and validation accuracy both increases. The validation accuracy increases more than the training accuracy. But for large models like ResNet 50, the validation accuracy actually is hurt by this way, okay, indicating that ResNet 50 is already a pretty large model. So we don't need to augment the model. It already have enough capacity. But by further augmenting the model, it may cause this overfitting problem. But for these tiny networks, we really need to expand the capacity of the model since the model is so small. And by augmenting the model, we can improve the capacity and increase the accuracy. And this method also works quite well for translearning tasks from ImageNet to Food 101, Flowers, Cars, Pets, Pascal VOC. Compared with knowledge distillation or just training more epochs, NetAug, which is this red curve, can consistently outperform the baseline methods by augmenting the model. And this is showing that NetAug also benefits the transfer learning. On top of the baseline, it can consistently improve the accuracy on different data sets. And also it can be transferred to object detection by reducing the max by 41% to 38% on Pascal and COCO data sets. And in summary, the network augmentation is a very effective and simple technique to virtually expand the capacity of a tiny model by adding this auxiliary supervision. At test time, we don't need any of this augmented model. So it has 0 parameter overhead and 0 computation overhead at test time. And all the code and details are available on our GitHub and website. So in summary, we talk about several techniques for TinyML and efficient deep learning for IoT devices, including MCUNet V1, the co-design of TinyNAS and TinyEngine to search the search space first and then perform once-for architecture search, followed by efficient inference, Tiny Inference Engine. And then we proposed efficient V2, which introduced a new patch-based inference method that can effectively reduce the activation memory and reduce the peak memory. And finally, network augmentation that can expand the capacity of tiny models and boost the accuracy at 0 computation overhead. Finally, I want to show some demos for the application for the TinyML applied to various applications, including detection, pose estimation, segmentation on the phone, and also GAN models. We can apply by using once-for-all techniques. We can edit the image rather than using 3 seconds. Now it's very responsive to change to photo edit by using the AnyCost GAN. And also we can accelerate the video recognition not only per image, but also have the temporal dimension where there's a lot of redundancy in the temporal dimension for tiny video understanding, and also tiny point cloud understanding to drive a car purely based on LiDAR. Since there's a lot of redundancy spatially, we can reduce the redundancy and also improve the speed by proposing this fast LiDAR net. And also we applied TinyML to do multitask learning for both detection and segmentation. Another example on multitask, both detection and segmentation. And also we expanded from multiple tasks to multiple sensors for both 6 cameras and also 1 LiDAR to perform 3D object detection. Okay, that's all for my presentation for TinyML and efficient AI. We hope to apply these techniques to make AI smaller, faster, greener, and more accessible to everyone. Thank you.
Thank you, Song. There are 2 questions in the chat. One regarding your deep compression approach.
Okay, so directions for device hardware designers with optimal memory size for specific ML applications. Yeah, that's a good point. Actually, we did a research in called the Neural Accelerator Architecture Search that can jointly search the hardware architecture together with the neural network architecture. The idea is that we put the neural architecture and accelerator architecture in the same search space to jointly design the neural net topology and accelerator architecture. So here we use evolution strategy to search among a hardware population and a mixed precision neural network population. And the highlight is that we not only search the numerical parameters, but also the non-numerical parameters, such as the connectivity and also the loop order. So such searched hardware compared with human designed hardware can achieve 4.4x EDP reduction by using the accelerator hardware architecture search, and another 2.7% accuracy improvement by combining it with neural architecture search. And such AI design hardware is quite different from human design. It chose to have an array size of 18 by 10. Data flow is KX parallel. R1 buffer size is like 419 kilobyte. R2 buffer size is 107 kilobyte. So the AI design data flow is quite interesting.
Excellent. Thank you. Really appreciate it.
Thank you. Another question is, how is network augmentation combined with knowledge distillation? So we can apply knowledge distillation while we are doing the supervision, right? Knowledge distillation just give you another loss, the KD loss. But for network augmentation, we just add another gradient, right? The gradient from the model itself, and also the gradient from the augmented neural network. So that's why it is orthogonal and can be combined together. And the code is also available on GitHub, so you can be welcome to try it out.
Okay, anyone have any other questions? You can unmute yourself and ask, or you could write it in the chat. Another question in the chat.
Oh, agriculture applications. We didn't specifically do agriculture related data sets, but I think these techniques can be applied over there, like detecting some crops or insects. But our models are all open source on GitHub. You are welcome to plug in your own agricultural data set and try the performance.
Cool.
Any other questions? All right, then thank you very much, Dr. Song Han. Appreciate you joining us today. And we will have our next Athena Institute speaker on June 17th, Professor Maria Gorlatova from Duke. So please join us then. Thank you, everyone.
Thank you.